Next, we have Karan Lulla, Senior Software Engineer, USA. Karan, based in San Francisco, California, United States, is currently an engineer at Apple. He brings experience from previous roles at Citrix, SAP, Xilinx, and Amdocs. He holds a master's in software engineering at San Jose State University with a robust skill set that includes development, NetApp filters, data on tap, FreeBSD, SDLC, and more.
Hello, Vanshi, can you hear me?
Yes.
Thank you for the introduction. Let me share my screen. Vanshi, can you see my screen?
Yes, it's visible.
Awesome, thank you. Okay, hello everyone. I'll be presenting the topic on design fault-tolerant test infrastructure for large-scale GPU manufacturing. This work basically tackles the challenge of ensuring GPUs are reliable for critical industries like finance, real estate, retail, and cloud computing. We don't want to have a single point of failure, as that could lead to huge financial losses or operational downtime. In this presentation, we'll explore importance of GPUs, a proposed architecture, a case study from Accenture, and future trends. So let's move ahead. Okay. So let's begin by understanding why GPUs matter so much today. In finance, they are the backbone of high-frequency trading systems that process massive data in milliseconds. In real estate, GPUs enable immersive 3D modeling for virtual tours, enhancing the customer-client experience. And in retail, they power real-time e-commerce recommendation engines that personalize shopping on the fly. This paper emphasizes on the AI-driven world, on the aspects of the GPU. So let's get. So what are we trying to avoid? So we are trying to avoid widespread disruptions, any halted trades, inaccurate models, which could lead to millions and sometimes billions in losses. So what does it take to build a testing system that can handle large-scale GPU manufacturing without missing a beat? The outline requirements are redundancy. So basically, redundancy will eliminate any single point of failures, ensuring there's a backup which would get kicked off seamlessly. Modularity, which allows a system to scale up or down as production needs change. And real-time monitoring to catch issues instantly. The fourth, and not the least, but automated error detection and checking, which would basically detect errors and quick fix them. So these elements work together to support a high throughput and reliability, especially under stresses like thermal variations or voltage spikes. Without them, there's always a risk of deploying faulty GPUs that could fail in the real world, underscoring the need for a resilient approach. Building on those requirements, here is a proposed architecture that we came up with. At the heart are the modular test cells that can be easily reconfigured for different GPU models. These integrate with cloud environments for remote scalable validation, allowing testing to be done from anywhere. And then the third aspect is the intelligent diagnostic system that oversees everything, handling faults such as thermal overloads, voltage inconsistencies, or computational errors through automated responses. This setup isn't just at a theoretical level, but it's designed for practical use in mass production, promoting resilience and minimizing the downtime. How did we implement this architecture? So the methodology that focuses on data-driven strategies, where test protocols are informed by real production data on the line to optimize accuracy. It includes edge case simulations to stress test the GPUs under extreme conditions like rare thermal spikes or power surges, ensuring any holdup on the GPU. So with continuous integration, pipelines, automated updates, and deployments keeps the system agile. And at the same time, predictive maintenance algorithms focus potential failures, while multi-level monitoring provides layered oversight for scalability. It's a step-by-step process that we have gone through and discussed more deeply in the paper. And then coming to the case study. So this was basically implemented at Accenture. They implemented an AI-powered fault-tolerant grid-based grid-based test system using the principles and the architecture that we just discussed. It allowed to reduce redundancy, introducing real-time diagnostics into the GPU validation process, and the results were pretty impressive. A 42% reduction in post-deployment failures, which translated to lower costs, fewer recalls, and greater client satisfaction. The real-world example proves that framework's effectiveness, showing how it can be applied in industries facing similar challenges. Looking to the future, we're excited that the trends are going towards self-healing environments that automatically detect and repair issues without human intervention. AI-driven bots do the root cause analysis, which would speed up troubleshooting and sustainable testing practices and minimize energy use and waste in manufacturing. In conclusion, the work offers a clear roadmap for GPU manufacturers to thrive in an AI-centric, real-time world. By adopting fault-tolerant infrastructure, we can build GPUs with high reliability with the growing demands in today's time. And finally, thank you all for joining me in this discussion on designing a fault-tolerant test infrastructure for GPUs manufacturing. As we wrap up, let's focus on the conclusions and the recommendations that can guide us forward. First, automated fault-tolerant infrastructure. This is about building testing systems that don't just catch errors, but prevent them through redundancy and automation. For GPUs powering AI workloads or real-time applications, reliability is non-negotiable. For example, imagine a self-driving car failing because of a defective chip. By automating tests and designing systems to handle failures gracefully, we boost uptime and trust in every GPUs that are shipped. And next, I would recommend embracing modularity. So modularity lets you scale testing setup as the production grows. And finally, cost savings, quality, and a competitive edge. Investing in the infrastructure cut repairs cost, like catching defects early. And companies can save up to like 30% on warranty claims and by doing the proactive testing. That's pretty much all from my side. Thank you, everyone.
Thank you, Mr. Karan Lulla, for your engaging and informative session. Your presentation on designing fault-tolerant test infrastructure for large-scale GPU manufacturing highlighted critical aspects of building resilient and scalable hardware systems. We sincerely appreciate your contribution to ICCCNet 2025.